Um, so, one thing. So how can we get like how can somebody tell how can we get a decent amount of accuracy without doing like much work, without doing much architectural changes? Like what is like probably methods where we can increase accuracy but not too much work?
Depends upon, like, if there is a high imbalance in the classes, then you can achieve high accuracy, but actually the model might not be performing that way.
Assume like a balanced data set.
Use a pre-trained model efficiently.
Use a pre-trained model, yeah. Pre-trained model, yeah. That's a good way. That's a good way. Is there a different one?
What sort of problem?
So pre-trained model is nothing but transfer learning. I mean, you can take that under the purview of transfer learning. So yeah, using pre-trained models transfer learning is one way of getting like decent accuracy without doing much work. But sometimes like what might happen is you might want to design architectures for like specific use case. Like ImageNet is one example where the task at hand is very specific and you want to keep designing better and better architectures. The reason is because every architecture that you previously designed will attain a certain accuracy but will saturate at one point. Like ResNet will probably achieve 80%, DenseNet will probably achieve 82%, and then you might want to get 90%. So that is motivation one. Motivation one is you want to design better architectures for maybe your purposes. Motivation two from sciencey perspective would be imagine someone gives you a task of like ID classification, a sprint task, and then it would be very nice if you could just go to your desk and press enter, and then next day when you come, you have a good architecture which is ready and you can just give. So that'd be nice, but yeah, it's like compute-wise, it's not feasible. So that is like second kind of motivation. But a serious second motivation is like designing these architectures is a bit hard. Like you need a lot of, so there are multiple things you can try out, and the search space of these architectures is very large. So it's difficult to like you need. It's not a hard science, but you also need to know where the skip connections go, what kind of filters you want to use, and do you use like regular convolution layers, or do you want to use depth-wise separable convolution layers, or do you want to use so this search space is pretty broad. So these are like major two motivation where you want to design a decent architecture, and designing of architectures is complicated. Today's paper, learning transferable architectures for scalable image recognition, is based on the idea that you can probably like back in the day, your major in at least in computer vision, what you would majorly work on is features, right? You would engineer features, and right now what you do is you learn the features by like deep learning or machine learning. So the premise of this paper is you want to do the same, but not for features, but for architectures. So instead of how we were doing the same things like 10 years back, how we were learning features, like how we learn features using deep learning. We want to do the same. We want to even learn. Let's not put manual efforts into designing architectures, but let's just learn the architectures. So how do you do that? Okay. This work builds upon the paper called NAS, Neural Architecture Search. So essentially, what this is, so it's like an RNN which they call a controller. So the controller will look like, so it will sample. Um, So you can think of this. So this is the main this is like the component which builds the architecture. I mean, you can think of this. You can think of this as the controller. Um, it is the controller. You don't need to think about it. It is the controller. So what you have essentially is a RNN, which will sample an architecture where the probability B. It will train that architecture and it will give you a certain accuracy, right? With that accuracy, using reinforcement learning, using the policy gradient method, you will update the controller. So that's essentially what the controller does. Now, this actually was this was presented in the neural architecture search paper. But the problem with but in the neural architecture search paper, what they ended up doing was that so the search space was really large, and also what they ended up doing in the last paper was I think using 800 GPUs. They trained CFAT models and ImageNet models, and I think they trained like 20,000 models if I'm not wrong, which they trained for 30 days. But in this paper, so the controller does 5 things. Let me see if I can keep this. Okay. Before going into what the controller does, I want to motivate one more thing, which is important. As I told you in the previous paper, they were like trying the search space was everything. Like they were trying 3 cross 3, 5 cross 5. So basically, their parameters were the parameters of the controller RNN were filter height, filter width, stride height, stride width. So that's what the RNN predicts. So if the RNN predicts that your search space becomes very large, right? Because the RNN can literally predict like whatever con filter you want or stride size you want. So that is very large. Now, the second motivation was paper I want. The second motivation, third motivation is so if you look at like these deep neural networks, right, like the successful ones, they usually have a similar motif in the sense that if you look at resonant, it's nothing but like a skip. A resonant is nothing but your 3 cross 3 batch normalization value and then your skip connection, right? Maybe 2 of those blocks and then you have a skip connection going to the second layer or any other layer. And that's an extension for like your 18 layers, 20 layers, 100 layers, whatever. Even dense-spread is nothing but your concatenation of all the features from your first layer, which gets connected to second layer, which all together gets to connected. Even InceptionNet is the same thing, right? You have your multiple small common blocks which get diversified and then connected, and then that same block is perpetuated again and again. So they observed that all these successful common block architectures have a similar motif. They have a simple cell which they originally create and which they stack multiple times. Now that's so taking that as inspiration, they have simplified the search space, which I will tell you in some time. But before that, previously, as we discussed, the controller RNN was outputting few parameters, con height, con width, stride height. Now they don't do this. So what the controller RNN ends up doing is so it predicts a cell. So this controller RNN will predict this single cell which they will stack. So the idea is to come up with a single cell which you can keep stacking. So they formulate 2 cells which they want to output. One is your normal cell, and another is reduction cell. Normal cell is nothing but it will take a feature map and give the same the size of the feature map will not reduce, and that is a normal block. Your reduction block is nothing but it will take a feature map and reduce the dimensions by 2. I mean reduce the spatial dimension by 2. It'll halve it, and it'll increase proportionately on the channel size. So normal and reduction. So this is now your controller RNN will take will output 5 things. In the sense that it will take the hi minus 1, output 1, output 2, and merge. So what it will do is it will take a hidden state. It will take um, um, if like whatever operation uh, whatever operation was done before, like let's say 3 cross 3 or 5 cross 5, it will take that, or the layer output before that, it will take that and something before that, and it will decide on 2 operations, one for this hidden state, one for this hidden state. It will select 2 operations. Now these 2 operations, if you look at the paper, they have simplified the search space in on page 3, if I'm not wrong. So it's either, so they have come up with like identity 1 cross 7, 3 cross 3, 5 cross 5, 1 cross 1 con, 3 cross 3 depth-wise separable, 7 cross 7 depth-wise separable, 3 cross 3 max pooling, 7 cross 7 max pooling, 3 cross 3 combination. So out of those, it will select one of the operations, and it will do that for like the hidden state 1. And another operation will select, it will do that for hidden state, the previous hidden state, and then it will merge those, like the merging operation on how to merge that cell. So this is what the controller RNN predicts, and yeah, and like once you get this cell, you stack them into like multiple. How many layers you want is your hyperparameter, like how many layers you want, and that's how they train it. I mean, depending on the task. So the way this is done is so they, like one more thing which is important in this paper is, so they do not train this on image, they train this on CFAR10, and so the whole network is trained on CFAR10 and they just transfer it to image. So the whole neural architecture space, I mean the search space and the model is trained on, is found on CFAR10, and it's just transfer learned on ImageNet. So this they do it in like 400 GPUs, 500 GPUs across 4 days. So the previous one was 800 GPUs in 30 days, and this one is 500 GPUs in 4 days. So if you look at the paper, I don't want to draw this diagram, it's very. If you look at the paper, not sure, page 5, if you look at their normal cell, page 5 normal cell, if you look at it, so you see those, so there are 5 blocks, right? So those are the outputs of your controller, and if you see, like the connections are very, like it would be difficult for a human to like intuitively decide, like the skip connection should go here in this branch and not in that branch. So yeah, so that's most of it. Few things about the paper are like how they use this, like controller is probably main, and the idea that you train it on CFAR10 and then transfer the whatever the best performing model of CFAR10, you just transfer that to image, and that also works. So that's yeah. Cool.
Yeah, like how does the update take, like?
For update, it's actually they use reinforcement learning. They use the policy range method. I'm not sure exactly how that works.
That was it.